All right, welcome back. I want to do the second half of our motion planning coverage here. So we talked mostly about optimization-based motion planning last time. And the other half, and in fact, a super important half in terms of what people use today, is sampling-based motion planning. So I'm going to spend the first part of the lecture on that. There's a couple core ideas that I want to make sure you've seen and I can land. But then I actually want to spend the end of the lecture bringing the two worlds of sampling-based and optimization-based planning together. So let's see how we go. Last time we talked about first inverse kinematics and then optimization-based, right? So remember, we were doing a lot of things in the configuration space of the robot, which we've talked about on and off, but in particular, I started drawing configuration spaces for you last time and trying to help you appreciate that they get ugly fast. The relatively simple geometries, right? So for even, I drew that really simple example of the two-link pendulum, right? And we had just two angles, so I could draw a 2D configuration space. And even that, you know, the collision-free region looked like this sort of hourglass-looking thing, which is this is, if I were to say this angle here was Q1, and this angle here was Q2, and I made a plot of the configuration space in Q1 and Q2, then these were obstacles over here. This is maybe joint limits up here, and the valid configurations were in the interior of that curvy hourglass kind of shape. And we said the goal of inverse kinematics was to kind of find one point in that space, right? Maybe that satisfies objectives like keeping your center of mass over your feet or reaching your hand into a particular location. That's the task already, an interesting task of trying to find a point in this sort of potentially complicated space that satisfies our objectives. But then trajectory optimization, in particular kinematic trajectory optimization, was just trying to find a sequence of points that could maybe transition between multiple configurations. Maybe if I wanted to pick up an object here, set it down over here, I need to find a curve through this space, and ideally one that stays completely inside the region so it doesn't bump into any obstacles for the entire trajectory. Okay? So the optimization view of that was, for instance, we'll parameterize our Q as a function of time with some parameter vector alpha, which I recommended for a popular choice is to choose this Bezier coefficients or this B-spline coefficients. You can, if you want, parameterize this with a deep network, or there's lots of other parameterizations you might choose. But this one we talked about had some nice virtues that, for instance, if all of the alphas were inside the region, in this case, let me not say that. More importantly was for joint limits and velocity limits were nice. It plays well with convex constraints. It actually doesn't play well with curvy constraints like that. So I want to not say that. Okay, but importantly, we could write an optimization that said, for instance, minimize the coefficients of my spline, subject to some objective, which I recommend some sort of simple objective, maybe shortest path or something like this. And subject to constraints that would look like our inverse kinematics constraints. Like, let's say the goal is at Q of alpha T final, and maybe the initial satisfies the kinematic constraints at T initial. Right, so I want you to be thinking about IK with this rich costs and constraints, and then kinematics as kinematic trajectory as optimization is just a richer version of that IK problem. But these are non-convex problems in general, and we had some fun last time sort of talking about that. I give you the really simple example of non-convexity if you have to choose to go left or right around an obstacle, which is easy to visualize if you're a point robot and there's a square obstacle or something you have to go around, but it also is happening all the time if I have to decide, you know, to go under the table or over the table, reach around my arm like this. There's all kinds of cases like this happens, and it can be very subtle. And we also had a sort of a fun teaching moment, right, where I put this in here, but where we realized that you know, kinematic trajectory optimization could actually stretch out the trajectory just so that the points don't, the points that you're checking don't land inside the shelf, but it actually is karate chopping the shelf in order to make that happen. Yeah?
Were you able to take steps so that you don't have to do it?
I didn't try. I don't expect to have, so the question was I able to fix it so you don't have an initialization? I think the kinematic trajectory optimization does not have any guarantees. I mean, maybe the fix will be towards the end of the lecture here. We'll have better algorithms. But the kinematic trajectory optimization using nonlinear optimization is going to have these problems. In general, you need to give it a good initial guess in order to be successful. Okay? Okay, so this fundamental problem of not knowing how to go left or right around the obstacle, right, is, in fact, somebody asked last time, so what if we sampled multiple initial conditions? Maybe we start sampling some initial conditions like this, sampling initial conditions like this, then we'll eventually find the solution. And the challenge is that in more complicated situations, there might be a lot of things you have to sample. So it becomes a challenge of coming up with the right sampling heuristics that will sort of guide your search. And it turns out there are some surprisingly simple and surprisingly good heuristics for guiding that search. Okay? And that's the stuff of sampling-based planning. Okay, so how many people here have heard of like RRT, PRM? Yeah. Okay, so there's a class of algorithms. They started getting popular in the late 90s, early 2000s that are based on this sample-based planning. And they were instantly popular because of the visualizations that they started to produce. So James Kuffner in particular, he worked closely with Steve Laval, who has got a beautiful book on planning algorithms. Okay, he started showing these kind of puzzles. Like this is a geometry puzzle, right? This is, I mean, literally, that's what you could buy it as a puzzle. But if you think about the configuration space of that task and finding a path that will get from a start configuration, you know, to a goal configuration, that is an incredibly hard search problem in terms of these pictures, right? I couldn't draw it if I wanted to. It would certainly look extremely hard. So that, for me, the first time I saw that was incredibly impressive. Made me want to know more. And then to almost simultaneously say, and it works for a whole humanoid, like in relatively high dimensions. One of the things I would immediately worry about when you start drawing samples and saying I'm going to rely on a method that's sampling in a configuration space, I'd be like, okay, but you're not going to solve that in 30 dimensions. And they sort of addressed that almost instantly, like within years of introducing the method, they were doing very high dimensions. So let me make sure I sort of tell you that story. There's really two core algorithms in the sampling-based motion planning world, and a bazillion variants, but two core algorithms. surveyed you about. One is the RRT, the Rapidly Exploring Randomized Trees. And the other one is the PRM. To play in this space, you have to use 3-letter acronyms. So you'll see we have a new algorithm that's also got a 3-letter acronym because we felt like we had to. Probabilistic roadmap. Okay, and they're both sort of surprisingly simple. Here we go. On the pseudocode for the RRT is like that. Okay? Here's the idea. You pick initial point at random, pick a point inside this Q1, Q2 space. Okay? Random config is doing doing one extra thing, which is that you instantly just check if that point puts you in collision. If it's in collision, you reject that sample. Okay? And if you sample enough, you hope to eventually find something that is in this collision-free region. Okay? And then, so that gives you 1 point. That gives you an initial point. Now I'm going to pick a different point. Let's say call it Q random here. And I'm going to take my current point, or my starting to get a tree here, and I'm just going to find the closest point to my new sample point. Here it was the Q near. And I'm going to grow a tree in the direction of this Q random. Okay? So the algorithm is, you have a tree. It starts off with a point, but think of the steady state where you've got an initial tree. Okay? I'm going to draw a sample at random, find the closest point on my tree, and add a new element to the tree that's in the direction of the sample. That's it. That's the algorithm. Okay? And it's incredibly clever. And I'll try to show you that in a few slides. It's incredibly clever because it has some important properties. It rapidly explores the space in ways that, its simplicity sort of hides its brilliance, I guess. Okay. Let me tell you why. Because here's a variant of the algorithm. Okay. So first of all, yeah. So if I just run that algorithm in just like a 2D space, okay, then this is kind of what happens. There's no collisions here. I'm just saying I'm allowed to pick any samples in the space, and I start with an initial point at the origin. Let me play that back for you a little bit more slowly here. Okay, it's not quite at the origin here, but I'm going to start, and as I take samples of this tree as it grows, it very quickly grows to all parts of the space. Okay, and then as it goes, it gets more and more looking in at the details. Okay, all from that simple algorithm. There was like nothing complicated about that algorithm, but it has this interpretation that it quickly fills space and then goes back and looks through all the details. So let's just appreciate how that happens. So first of all, let's take an almost identical algorithm, but just a little bit simple, which is I'm going to pick a point at random. Okay, I'll take my tree. I'll pick a random point in my tree, and I'll grow it in a random direction. It sounds almost identical. I'm going to pick a point in my tree, grow in a random direction. If you do that, and you start at the start and start growing in a random direction, this is what you get. You get a random walk around your initial condition, and it generates hairballs, basically, around the start, and it does a very bad job of exploring the space. Okay? So a random point in a random direction doesn't get it done. The heuristic that's happening implicitly here in the RRT is it's picking a random subgoal, which might be anywhere in the space, and it's using that subgoal, at least for one step, to try to grow into a new region of space. So picking uniformly in the space gives it this sort of expansion property. And the sort of more rigorous interpretation of that, you can argue that RRTs have what's called the Voronoi bias. Okay, so do you know what a Voronoi region is? This illustration here is the Voronoi regions of the graph at every instant in time. So a Voronoi region is a decomposition of the space where I'm making a region. Let me pause that just so I can point at it. Maybe I'll even just draw it here. Let's say I have a handful of points in the space, okay? The Voronoi regions are the regions, for every point, there's a Voronoi region, associated Voronoi region, and that's the set of the space that is closest to that point by whatever distance metric you're operating in. So the Voronoi regions in a Euclidean metric will always partition, have lines that partition exactly between 2 points, okay? So something like this is the Voronoi region associated with that point, okay? And then similarly, there's going to be a Voronoi region for this point, and a Voronoi region, these things, yeah. Okay, so every point has an associated Voronoi region. These are the set of points that are, a set of elements in the space here that are closest to that point. All right? So you can see here, this is an RRT while it's growing in the red and the blue, okay? And I've drawn the Voronoi regions associated with its current state of the graph. Now here's the claim. So if I sample uniformly in the space, then the probability of sampling a region, which is equivalent now to the probability of growing from some point, right? You're going to be the nearest neighbor if the random sample landed in your Voronoi region. The probability of landing in, let's say, this guy's Voronoi region is proportional to the volume of that Voronoi region, okay? So the big Voronoi regions are more likely to get sampled, okay? And so the points associated with that are more likely to get grown. And at the beginning of the expansion, the elements that are sort of on the fringe of the region are going to be these massive Voronoi regions. So with very high probability, you're going to sample one of those big regions, and you're going to expand out into space, right? And then as you go, you start filling in all the big regions just with probability. I'll just finish this, and then suddenly the regions that are sort of in the middle here that were less volume than the outskirts until they become the biggest ones, and then they'll eventually fill in the details on the inside. Yes? That's true. Yep. It's not unit distance. So the question is, like, how far do you expand? That's a parameter in the algorithm that people have heuristics for that. But there's no magic number there, and the argument doesn't explicitly depend on that. Yeah? So 2, I don't know. It's just a random number that people will parameterize. It tends to be a constant, and you tend to, so again, you want to check collisions on the segment. So you'll try to sample finely for collisions in the length of the segment and just expend a little bit. Yeah? Yes?
So like the point you sample is closer than
That's true. If your sampling point is so close, you can just extend the whole way there. You wouldn't necessarily pass it. Yes?
And so we are keen on like exploring as many like regions, like points as we can, so that we don't get stuck in a
So you'd like to find, so we would like in this plot to be able to find paths to the goal that went this way around, right? And then, so this is not yet saying anything about optimization. This is finding any path. Yes. So if there's a blockage over here, right? I might have to sample all the way here, but then actually give up and go around and go the other way. Yeah.
why do I have it why do I have to go to like another approach would be to first sample point uniformly
Yes.
by space
Yes.
and then go to like sample uniformly the point and then just say for every point I have give me a random nearest neighbor and then okay I wouldn't have a tree at that point I guess but like I would still have some kind of
That's the other one. You're right on. You're right on. But that's the other one. It's a good idea. It's a good idea. Yes. So I actually came up with an example to try to make the point here too. So here's a harder motion planning problem where you start in the inside and you have to find your way over to the goal on the outside. Okay, so this is a bug trap, they call it, right? So it's just like a fly trap where you try to make it, sort of easy to come in, but hard to find its way out. Okay, but these, even if there are narrow passages, the sampling-based planners can sort of famously can be slow in narrow passages. You might have to wait a long time to find a sample in the narrow passage. Okay, but amazingly, probabilistically, they will eventually find a sample. And in this case, they might have to find many samples in a row to eventually work their way out of that narrow passage. But they will do it with probability 1 as the number of samples goes to infinity. That's the claim. Yeah?
This may be like a more of an explanation of what I'm saying, but it seems like if instead of going a fixed distance from your nearest neighbor, if you just go straight to whatever point you're sampling,
Yep.
then you would explore faster. Is there a reason why we don't do that for RP?
Yeah, I think that there's all kinds of heuristics and implementation details. I think you don't typically want to take straight line segments for really long paths in configuration space, for instance. So I don't think there's anything wrong with that, but I think people having banged on it, have found better performance when you don't extend the whole way. Yeah. You also, of course, you want to check carefully along the line segment, and maybe that's an easier thing to feel comfortable with a small amount of samples, in a small extension. Yeah.
Other than the techniques that case difficulty do in the case you have choke points such as
Zero measure is a different game. So if you really had a zero measure, like a line segment that was the only feasible solution here, then this algorithm out of the box would not do very well. You would need to explicitly have a sampling that could draw samples from that distribution. There's a lot of work people have done of trying to do. It comes up, for instance, if you're doing bimanual or task space sort of motions that have some sort of constraints, people have ways to project the samples onto those constraints. But this out of the box would not do well with a zero measure. It needs some sort of finite measure. I would not say, I think the algorithm is like 4 lines long. So there's not a lot, I mean, really, and the implementations, the difference between a MATLAB implementation that takes you 2 minutes and a professional implementation is, doing really clever things, interacting with the collision detection and stuff like that, but really the algorithm is fundamentally pretty simple.
Yeah, I guess to follow up on that question. So how do you make sure what is the fastest where every intersects with something but it's not true? It's definitely more likely to have bigger chunks, but maybe small ones with two boxes. Do we just every time we try to add a point, we try to keep it?
Oh, I see. So you could have branches that cross. That's true. I don't think there's typically not a careful checking about avoiding crossing. That would add, you wouldn't actually call it apparent. You wouldn't make a connection on the cross, right? So in the, it's a pass through or something like that. Yeah. I mean, there's a definite tree structure. Vertices have a parent, right? And you wouldn't consider the one that you happen to go across as a parent. So it's still a tree in the data structure sense, right? And it doesn't really affect the algorithm. I think it would probably be more expensive to check it. Yeah. Okay, so there's so the basic claim of this algorithm is that if a path exists from the start to the goal, and there's with positive measure, okay, then it will find this with probability 1 as the number of samples goes to infinity. That's a super powerful thing to say, but infinity is a long time. So in practice, you run lots of samples. This is very cheap to run, and you can run it at scale. You can sample in parallel and all these things. Okay, this is a surprisingly effective algorithm. There's a bunch of different variations. So probably if I had a goal here and a start here, I wouldn't actually do what I've shown. I would actually probably grow an RRT in both directions, from the goal backwards towards the start and the start forwards towards the goal. That way my forward tree doesn't have to find a needle in the haystack. It can connect anywhere and that's where you do start connecting for neighbors in the other tree. But you're looking at vertices, typically not at the edges of the other tree. As you say, you check that. And there's a bunch of heuristics, like you could say maybe with with probability 0.1, I will use the goal, the true goal, as my sub-goal and try to extend towards the true goal, right? I'll pick a sub-goal at random with probability 0.9, you know, and a probability, choose the true goal with probability 0.1. And there's a huge list of sort of heuristics like this, and people have really done a lot of work on that, okay? But the core idea here is we're addressing the non-convexity of the problem with sampling. Okay, so the other version, already alluded to here, is particularly useful. So when would you want to think about a graph instead of a, you know, and maybe just sample a lot of times beforehand? In particular, in applications, you might want to do that if you're going to solve many motion planning problems in the same environment. That tends to be the thing. If you're sort of finding, if you're in a new environment every time and you want to find a path from the start to the goal, people tend to grow a tree forward and a tree backwards and just do this single query planners. But if you're going to be like a robot operating in the same environment all day long, then it makes sense to just build a dense graph, okay, and run many queries online in that graph, okay? So the probabilistic roadmap is now a roadmap, a graph of possible edges, and the algorithm is similarly extremely simple. You pick a point at random, okay? This one explicitly said, check that it's collision-free, okay? And then every time you add a point, you're just going to add, you're going to check for its nearest neighbors and just try to add a line segment to all of the nearest neighbors, as long as the line segment is collision-free, okay? So you end up with, if my obstacles are in gray here, this is a very sparse PRM. In practice, they tend to be much more dense than this, okay? I'll start drawing points at random. I'll check every time I add a new point, I'll check for some nearest neighbors. And if I can make an edge that connects to that nearest neighbor, then I will make that edge. Sometimes the nearest neighbors are based on distance. Sometimes they're based on number of nearest neighbors, okay? But they're always based on data structures like KD trees and the like to make that efficient, okay? And you end up with a sort of roadmap, a graph. Yes? You sample densely, typically. Sometimes people will do careful checks, doing swept volume kind of calculations, but it tends to be sampled densely. Yeah. Almost always. Was that roughly your proposal, or yes? Okay. And then when you have a new motion planning query that comes on, maybe a new start and a new goal, then your job is reduced to finding hopefully a very short line segment to get you back to the graph, finding a segment to get you from the graph to the goal, and then you can solve a simple sort of shortest path on the graph problem to get you from the start to the goal. Okay, and you can do this, and then you might as well add Q initial and Q goal to the roadmap, and then keep going, and your map gets stronger, and you plan quickly on the fly. So this works. I mean, people deploy this all the time. There's a company, Real-Time Robotics, that they started off by putting all these on a chip and having interactive rate planning with people in the loop, for instance. So what they would do is they would build a collision map, basically an occupancy map of possible places in the world that the robot shouldn't collide with quickly, like on the fly from the depth sensors. Okay. Someone's going to walk into the space here in a second. They plan on the fly. And importantly, I'll skip ahead here. They're happy to do it with real-time changes in the obstacles and the like. The video's not playing very well. It's not showing the real-time nature the way I would hope, but so this is a company. You can buy their product and do real-time motion planning. I'm pretty sure they're all CPU-based and not chip-based anymore, but this is a real thing. Companies deploy this often. They were originally ASIC, I think. Yeah. Yeah. And there's a wealth of code out there in the open source. So the OMPL is the Open Motion Planning Library. It has basically, every once in a while, the research community will sort of get behind a project and get to the point where, like, every time you write a new motion planning paper, you must compare your results against the ones in OMPL, for instance, and then there was a great incentive to sort of contribute your code into the Open Motion Planning Library. And so there's a really nice sort of library of the different offerings in the sample-based motion planning world available in OMPL. And people have definitely connected OMPL and Drake if you want to try using those in your project. And if you look, there's like a huge list. This is the OMPL documentation, a huge list of multi-query planners, variants on the PRM, for instance, single query planners that are variants on the RRT. Okay, there's a handful of different ideas out there, but they're really based on these sort of core ideas. Okay, long list. If you want to, add to the list, you should, right? Okay, so yes, please.
How do these systems do when
Uncertainty, is that maybe a fair way to say what you're saying? Okay. I mean, there's a few ways that that sort of variability could enter the task, right? If it's an obstacle that's moving, then your configuration space obstacles might be moving around, right? And people will do things like, imagine you've spent a long time computing a probabilistic roadmap for your 10-dimensional system, not a long time maybe, but a few minutes of computation sort of to build up a nice roadmap, and now suddenly somebody shifted, we always joke like when, I'm a huge fan of theorists. I would never, but I also do experiments, and you can sort of tell when a theorist comes in the lab because they'll like lean on your camera, and you're like, I got to recalibrate the camera, So imagine you've carefully done everything about to compute your roadmap, and then, someone comes in and just moves something in your robot setup, and you're like, But people do there's a lot of sort of wisdom about, trimming a few edges. You could very quickly modify your roadmap, right, in order to accommodate that. If you have different goals in configuration space, right, dealing with perceptual uncertainty is a separate question. We'll address that more later. But I think different goals and sort of picking the hammer up at a different place if it moves, that seems to fit right in. That would just be a different goal in configuration space. One of the things that, this is a nice transition to what I want to talk about next. So one of the things that trajectory optimization did extremely well that the sample-based planners don't do very well is, when you've parameterized a trajectory, you can very naturally put, in optimization world, you can naturally put constraints on the, let's say, the curvature of the trajectory, the smoothness of the trajectory, the velocity that you're going to execute that trajectory. These things are less natural in the sample-based planning world. You tend to do line segments between points because you don't know, let's say in the PRM, you don't know where the start and the goal is going to be. So you don't really have more information than let's just think about the straight line segment. And then when it's time now to go and plan, the only thing you've actually certified ahead of time is that straight line segment. So there's not really any room left to do something better like smooth optimization. So people do heuristics to try to refine a path. So they might find a path that's a little circuitous. There's something we sort of comically refer to as the RRT dance, right? So every once in a while you'll see a robot that's like, going to go from here to here, and it goes, like something like this, and then puts it down, right? And you'll see that like in professional robot videos, and you'll wonder what the heck's happening. And it's because it was based on a randomized motion planner, and it took, a slightly circuitous path to the goal, okay? So people have heuristics that will shortcut and try to clean up a PRM after the fact. So they tend to be very simple heuristics that work fairly well, but they still don't give you great smooth paths. If you wanted to like put continuous, if you really had like dynamic constraints, if you're a quad rotor that can't take arbitrary directions, or if you really care about like torque limits, velocity limits, and other things like this, you have to sort of shoehorn those into the randomized planners. Yeah.
I think you previously mentioned that RGT and these methods also go pretty well even for high-dimensional systems. How does that work out? Because we have a higher dimension, like 30 degrees of freedom, humanoid. Obviously, the configuration space is much, much bigger, and the projections are much, much more compact.
Yes. So, well, first of all, if we're in a 30-degree configuration space, out of the box, that algorithm seems like it would be unlikely to scale. But I think that this rapidly exploring property and its ability to go into corners, this sort of Voronoi bias, scales surprisingly well, beyond what my geometry of 30-dimensional space in my head would permit me to expect, right? But really, these things can solve problems. RRTs can solve problems in high dimensions. PRMs tend to not go to high dimensions, not as high dimensions. You probably wouldn't spend time trying to completely cover the space of a 30-dimensional configuration space, right? But for a one-time plan, it tends to be a little bit more important than to give strong heuristics to kind of pull your solution in the right direction. So with probability 0.5, maybe I'll move towards the goal or something like this. That's the simplest way to pull me. But the RRT does scale better than I would expect. Yeah. Yeah. Sorry. You end up with sparser trees. I don't know that yeah. Okay. The high-dimensional geometry is very weird, right? And there's important properties like, all our sort of intuition about volume and stuff like this breaks in high dimensions. So your question is, are the obstacles sparser in high dimensions? I think that's a good question, because I could also argue that the obstacles are somehow bigger, or the configuration space scales. Yeah, I don't know if there's an obvious exchange in that direction. Yeah. Yes.
What are some ideas to smoothen out the path after you actually
Yeah. So I say the most common ideas to smooth out a path are actually pretty heuristic. So a standard sort of shortcutting, they would call it. Maybe shortcutting. Imagine I found a path, and it's inspired by paths that come out looking like this, for instance. So imagine I was taking a path that did something like this. Okay, that's what came out of my RRT, right? There's really no reason why it shouldn't. A standard thing to do would be to take now just the points on your path, and then spend a little bit of time, pick 2 points at random, any 2 points at random, and try to connect a straight line. If that straight line is valid, then cut that one out, okay? Pick another 2 points. Maybe you get really lucky and you just go like this, and then, you got a real nice simple path, okay? And in practice, that's, I would say, the most common simplification strategy that people use, is just the sort of, yeah. Yeah. Okay, so now if you care about continuity constraints and stuff like this, then I think I would advocate that you would solve a small trajectory optimization on the fly. So use the RRT as an initial guess, okay? And now just hand that to a trajectory optimization and clean it up. And in fact, I referenced in the notes that we have the one that we used the most in the sort of, let's say, the TRI dish loading demo, but in other demos too, was an anytime trajectory optimization that you'd get your RRT out, okay? You'd start executing immediately, but it would be just smoothing. It'd be doing as many passes of trajectory optimization as it could as you were running along the trajectory and giving pretty nice smooth paths out. So in both cases, you're going to have a limited sampling density unless you do something smarter, right? You're only checking collisions at limited numbers of samples. You could parameterize a trajectory optimization that could start with the line segment, but have the flexibility to try to get smooth as it optimizes. But every step of that optimization is going to have to check those constraints at some finite numbers of samples, right? So there are things you can do that are better. Let me just sort of storyboard one of them. Imagine my robot is in this configuration at time, or at one point in my sample, and there's another sample I want to connect to that's in this configuration. Okay, so sometimes people will take the convex hull of those two. This is not a sound algorithm. It doesn't completely avoid collisions, but you can potentially do better if you take the convex hull of the geometry at both of those samples, right? And check that for collisions. That's more expensive, but a little bit safer. Now, of course, if you think about the geometry of that, the path that this will take could leave that convex hull. There's no guarantee that the convex hull will be an envelope of the entire motion. Okay, but that's a common heuristic if you want to try to be a little bit more careful, these swept volume kind of computations. Okay. Cool, okay. So RT, sample-based planning and trajectory optimization have both been wildly successful in different applications. But they both have some limitations. And I've always sort of caught a thought, well, shouldn't they be able to work a little better together? And why are they so different, right? So we've been doing work in my group lately to try to bring those two together. And I wanted to tell you about that for a few minutes here at the end. So first of all, I made a video, or I found a video that had a good RRT dance. Let me just show that before I go on. This is the famous PR2, yeah? Okay, this is the RRT dance. And, you would think nobody's going to release a video with that, right? This is them, of course, intentionally saying they can do better with the RRT star algorithm, okay? But I didn't want to put it in here, but I swear the people that make a product that sell sampling-based motion planning, solutions, their promotional videos look like that. So it really happens in real life, right? Like you see robots move like that, and you think, oh, we must be able to do better, right? RRT star does better. So you can do there's a version of the RRT that will continue to add vertices and try to prune inefficient vertices as it expands, and will asymptotically converge on optimal paths, okay? That is one algorithm that I chose not to dig into too much, but that was the one that had this paper that shows that they could do better. Okay, but let's think about how can we connect the good things about sample-based planning, which is its global search capabilities, with, I think, the good things about trajectory optimization, which is its ability to handle dynamic constraints and continuous curves, okay? It seems like doing one stop and then doing the other is leaving something on the table. There's really no sense in which the path I found from a random search is the right path around the obstacle. It might be that once I consider the continuous constraints, I really should have gone the other way around the obstacle. That would have been a shorter path. So if we can make a sort of a deeper connection between them, then we're going to hopefully be in a better place. All right, so we've been trying to do maybe the harder thing you would think. So let me go back to my red square example here. So I had a start and a goal, okay, and I had a red obstacle here, and I wanted to find a path. So one idea is to try to explicitly address the combinatorics of the problem, okay, by saying, well, certainly there's a path over here and there's a path over here. But actually, it's a little bit easier to try to do a convex decomposition of the free space, okay? And there's subtle reasons why that might be better, and there's lots of ways you could choose to do this. But let's say I did something like this and said, this is one convex region. This is a good place to go, okay? Here's another convex region over here. Here's another convex region over here, and another convex region over here, okay? I want to tell you about a set of tools that can sort of explicitly check all of the, make a sort of a graph search that's saying, should I go this way or should I go this way? But solve the trajectory optimization at the same time as it's solving the graph search. Okay, and the virtue of that is that we can now do more global trajectory optimization. So there's this idea, we call it motion planning with graphs of convex sets. The paper actually is just about to come out, but we say motion planning around obstacles with convex optimization. Okay, and now you guys have heard me talk about this enough, and when you think about the non-convex landscapes that we're talking about in motion planning and obstacles and things like this, and you hear convex optimization, that title's supposed to be surprising, that you shouldn't expect convex optimization should sort of be able to solve these really non-convex problems. But we're hoping that we now have algorithms that can find better plans faster than the sampling-based planners, but avoid some of the local minima from trajectory optimization, can try to guarantee that paths are collision-free, and they handle the dynamic constraints that we want, and hopefully scale to really big problems. Yeah? This is MIT, primarily, yeah. And so the way to do it is to make these sort of decompositions. It's not for free. You have to do some work up front, the same way you do the roadmap work up front to sort of analyze the space and build a graph. We're going to analyze the space and try to find convex decompositions of the configuration space. But then once we do that, we can write a pretty natural graph optimization, which says, maybe I go from my source to the region on the left, and then to the top, and then to the target, or there's another path that goes through the bottom, through the right, to the top. And through a convex decomposition of the space, we can sort of enumerate the possible paths through the configuration space and search them, in a more principled, maybe a more efficient way. And what's hopefully surprising is that we can solve pretty complicated problems. This is one of my favorites. So this is like a mug swap with two arms that are put way too close together. We wouldn't have done this in the lab, okay, quite. Right? And so it's solving a pretty hard motion planning problem, but it's solving it with a convex optimization approach that uses the sort of graph decomposition. Now we do put it on real robots in the lab, and I'll show you some examples of that in a few minutes. Okay, so here's the idea. It's pretty simple, I guess, but just to remember the sampling-based motion planning picture from the PRM. What we did here is every time we picked a point at random, we tried to connect to its neighbors. And like I said, all we had certified at roadmap construction time was these line segments. And that sort of doesn't leave enough room to do the optimization at runtime. So the proposal now is every time I pick a sample, try to do a little bit more work and grow out a region around that sample in configuration space. And that region gives me space to parameterize a curve and have some room to do optimization on the fly. Okay, so instead of a picture like this, we're going to have these pictures like this, where we have obstacles here, and we have big convex regions in configuration space. Okay, and then we're going to try to find paths, continuous curves that go through those convex decompositions. Is that okay? It might not be, I put this in intentionally, depending on the way, how much you know about your geometry, the same sort of probabilistic completeness that you have in a sample-based planner. You're going to have a probabilistic coverage of the configuration free space based on the number of sort of regions you're going to use to try to fill the space. Yes?
So I think all the methods we have talked about today are built upon the assumption that you perfectly know the configuration space. But what if in some cases you do not exactly know the projection of your object into your high-dimensional configuration space? How does this work? So can you still obtain a convex composition or something like that?
That's a great question. So yeah, so the motion planning, and this is partly what I said last time, and I'll say again at the end this time, I don't love the everything is known, collision-free motion planning, don't touch anything in the world, but that is the formulation we're starting with here. Now the way we address that is we start putting in more machinery for trying to plan under uncertainty, right? So if I say, typically I would say that I would use a ball of uncertainty around my trajectory as a surrogate for uncertainty about my obstacles. That tends to be more tractable, but you can do either, right? You can put uncertainty on your obstacles and stuff too. And so tools that try to reason about uncertainty do fit in, at least in the trajectory optimization framework. They could do it. You could do that in. Yeah, you can certainly do sample-based planning in belief space, but that's a tougher road maybe. So that's a great question, and that is. Let's just say for now that's a limitation of what I'm saying right now, is that these are assuming known configuration space. Absolutely, yes. Good. So if the yep. So we are going to try to take so convex decompositions of the space. So and we're typically going to represent them as polytopes, although other choices are possible, but always a convex set. It is in task space. It's sort of reasonable to assume that the geometries are convex. Like I could take my robot and do like a convex decomposition of the robot, and that's totally fine. But I think you're right. It's in configuration space, things are curvy, and I should absolutely not assume that those are curvy. So this picture was the simple example, but in general, I want to think about being collision-free of objects that have curved surfaces. Absolutely. Okay, but it's a different question about what your obstacles are shaped like versus what your regions you're trying to stay inside are shaped like. And we do typically keep our regions simpler. Yeah.
Is it happening every time? Like, what if your environment is
Yep. They're the same way that you would, this is very similar to the PRM, where you spend a lot of time up front doing a roadmap, so you can do many queries online. If someone walks into your space, then the first line of defense would be to just trim elements of your roadmap or trim your convex sets in order to account for that. If that takes away feasible solutions, then you might have to repair and try to do some online thing. But yeah, I think the benefit would be that you can do some of the harder computations offline. Yeah.
Seems like you are like the configuration and so what you're doing is you're converting a smooth space into a non-smooth space, so that's like complex decomposition, in order to do smooth optimization. And so wouldn't there be better like partitions? For example, ellipses, that would be smooth.
Yeah, good. That's a really good question. So I think there are elements, I'm sorry that the projector's flashing, I don't know why that is, but there are elements of the space that are certainly smooth. I completely agree with you about that. I don't think that the configuration spaces are smooth in general. You can have, you can have these surfaces intersect in very complicated ways in high dimensions. I think there is I think the essential element, which I believe strongly in, is that there's a combinatorial problem in the space of trying to decide left or right around obstacles. If you have a series, like a forest of obstacles, you have to decide potentially a combinatorial number of paths around the trees. I think that is the essential element that trajectory optimization has struggled to capture. So decomposing that in a graph and bringing tools from combinatorial optimization, I think is a correct way to target that hardness. You can make different choices about the shapes of your sets and things like this, but I do think bringing in combinatorial optimization is the natural approach. And the sampling-based approaches are doing that implicitly, right? They're using a sort of a graph-type structure to handle the complexity of the space. But I agree with you. Locally, things could look, you could try to run up, and when we're using this for planning through contact, we have to think more about trying to line up with the contact surfaces nicely. Okay, so the PRM is a roadmap of vertices, and this thing we're calling graphs of convex sets, GCS, because we needed 3 letters to play in the space, is a roadmap of convex sets, okay, with continuous curves inside them. All right, so this is how it works. So the first thing we have to do is we have to do an approximate decomposition of collision-free space. The name of the first algorithm that we did in this and we continue to use is IRIS, iterative region inflation by semi-definite programming, but we all just say IRIS, and we say it so much that if I figured I had to put it on this first slide because I will say IRIS without thinking about it, and I wanted to make sure I define it once, okay? And then we have an algorithm that's for efficiently solving shortest paths on these graphs of convex sets. Okay, that's sort of the 2 prerequisites. And putting it together is trying to show that we can transcribe the motion planning problem of continuous curves with time scaling and everything into this trajectory optimization problem into this graph of convex sets using the iris regions. So I have a few slides and pictures I'll draw on the board to talk through that. Okay, so so the first thing is, how do you do a convex decomposition of these potentially terrible spaces? Okay, I think there's let's start with thinking about a very local approach. Okay, so if you give me a sample point, and we're going to take this sort of analogy with PRM seriously. You give me a sample point. There's a lot of potential obstacles in the space. Okay, what we're going to do is try to find separating hyperplanes. That's a standard way to make a convex set. I'm going to take every possible obstacle in my space, and I'm going to find a separating hyperplane that separates me from that space. Okay. Now the family of possible separating hyperplanes will define my convex set. And then the question is just, which separating hyperplane should I use? Like at what angle should I set my separating hyperplane? And we use this inner ellipse to try to sort of push out and define a notion of volume inside this set. So there's an iteration where it finds potentially a small set of separating hyperplanes, so a small region, and then it computes a volume, and it makes it bigger and bigger and bigger in order to shove out and try to make the biggest possible local approximation of the convex configurations free space. Now, the original one only worked in sort of a Euclidean space, not with curvy geometry. We assumed the obstacles were convex, but now we can do it even in the sort of non-convex space using either nonlinear optimization, which is fast but approximate, or a sort of some of the algebraic kinematics I talked about the other day to try to do a rigorous certification with polynomial optimization. Okay, so the picture here is two arms moving in a configuration space with most of these links locked so that I can make a two-dimensional plot, Q1 and Q2. So the collision space is in red, and we find these sort of convex decompositions, okay, using a variant of that iris type algorithm. Okay, we're going to have you play with a simple version of iris on the problem set, I believe. Shows that. Next problem set. Okay, so remember this example from last time? This was my double pendulum that I put down, and this is the hourglass sort of configuration space. It's actually funny. I've really got to make better figures. I was like, what's the best way to make all these figures? And if I run the unit tests in Drake here, so when I wrote the code for Drake for this, I made a battery of tests that were just trying to make sure, tested in all these weird configurations, and I put some visualizations in there. And the best way I have to show you that now is actually to run those tests. I'm going to make them pretty and put them in the notes, hopefully tonight. Okay, here's my hourglass. So one thing I don't like about Meshcat uses Three.js, which uses lines and none of the browsers support line width. So there are always these like super skinny, hard to see on the board lines. It drives me crazy. So I'm gonna have to figure something out about that. Okay, but this is the hourglass sampled with an iris region, and this is just the unit test that runs when you run iris in configuration space in Drake, and it finds this nice big green region. Okay, but if you look, I have a bunch of different sort of tests. There's a really curvy, complicated configuration space here. It actually goes all the way to here, the blue. Okay, this is a multi-link sort of object trying to move around. Okay, and it finds this nice big green region here with this simple seed. Okay, this one shows that it's not perfect, and it's actually really hard to, so there's two versions of the algorithm. One is this non-convex optimization. The way it works is it basically tries to draw samples from the configuration space that are inside the proposed volume, and then try to find a counterexample. It tries to find a point inside that's currently inside the region that is also in a collision. Okay, the sums of squares one is tight, and it's just more expensive to run, but it will be certified up to numerical tolerances. Okay, this was an adversarially chosen example where the blue region is the true configuration-free space, and actually there's a point that's outside the space because it's exceedingly hard to draw a sample down here for which the ellipsoidal metric that we use for volume doesn't pull the sample over here to find a counterexample. So this was like a carefully designed example that shows that the system's not always tight in the nonlinear optimization. Okay, but most of the time in practice it does a pretty good job. And you have just like in the sampling-based algorithms, you have a threshold where you basically say the number of counterexamples that you want to fail to find consecutively before you say you're done. You basically say, if I tried finding counterexamples for like 10 counterexamples in a row and I didn't find any, I'm going to call that probabilistically certified. And that number 10 is a parameter that you get to play with. Okay, there's more, but I think you get the point. Okay, so so we have this sort of initial iris decomposition algorithm. And what's surprising about it, I think, is how well it works. So this actually was a dynamic obstacle, so just like you guys were asking about here. So the original iris regions were only done using the arm and the shelves. But then on the fly, we have a mug inside there, so we actually trimmed the region on the fly in order to shorten that, but didn't optimize it. Okay? But the configuration-free region that's around that obstacle, this is, so you have to say, okay, I've got a 7-dimensional configuration space. How am I going to draw the iris region for you? This is not probably the best we could do, but this was the idea of the day, was to just do a random walk inside that region just to show you that it's kind of big and that it goes right up to and around the mug. Right? So you might think all the interesting places of your configuration space would not be covered, but we found that is not true. And even when you're in doing interesting things, these iris regions tend to be big and useful. Okay, so that was something I couldn't have guaranteed, but we were very happy to see, and we see repeatedly in practice. Okay, so if you took the PRM analogy completely at face value, then the way you would do it, you would pick a point at random, grow a region, pick another point at random, grow a region. But actually, that's not the best you can do. You can do smarter things by trying to do an efficient cover of the entire configuration space. So here's one idea that I'm particularly fond of for doing that. So we're going to do something like a PRM at the beginning. We're going to draw a bunch of random points. A visibility graph is almost the PRM, but we're just going to forget about the nearest neighbor part. Just try to make any possible connection. So if I when I add a point here, I'm going to connect it to any other point in the graph, no matter how far it is. I'm not worried about efficiency or anything. I just want to cover as much as possible. Now, I have a discrete graph here. And the observation is that the cliques of the graph, so in graph theory, what a clique is the vertices that are all connected to each other. They're clumps of vertices that are all neighbors, right? The cliques in this visibility graph have a correspondence to the convex regions of the space, right? You could have an obstacle inside here. It doesn't certify anything. But there's a natural analog, the sort of the cliques of a densely sampled visibility graph. This is a sparse one just to make the picture simple. But as you get to a denser visibility graph, the cliques are the natural discrete correspondence to the convex sets. This we can do at scale and find maximum cliques, or maximal cliques, but we actually can find maximum cliques. And then at each of those cliques, we run the iris algorithm with that as an initial guess, to find the local large region and try to certify that it's actually collision-free, that there's no holes in the interior or things like that. Yeah? What's that? You're saying that there's NP completeness on the... So good. So max clique is NP complete. That's why I said or maximal clique. But actually, it is NP complete, but the coefficients are not bad. These problems solve... we weren't sure if it was going to be able to solve, but every problem we've thrown at it, it solves very, very quickly for these size graphs, even with thousands, of vertices. Yeah, it is officially NP complete, but its growth is modest. Yes. That is the definition of visibility graph. Yes. Good. Yeah. So if I had here, I could have had an obstacle in here that I just completely missed, right? So that's why we run iris at the end. So we do the final step of continuous reasoning that's trying to in the sums of squares version, certify absolutely that it's not in collision. Okay, but in the nonlinear one, it's just doing counterexample searches. But we do continuous reasoning over the entire space as the final step of the algorithm. This is just got to be strong enough to be a heuristic, a good heuristic for where to put the sets. I'm going to repeat just for the microphone, but the claim is that cliques in this graph are a good initial guess for where to look at for convex sets. But we're going to still run our careful continuous convex set algorithm at the end. This is just a decision of where to look more broadly to get good coverage of the convex sets. Yeah. Otherwise, you'll get lots of convex sets that overlap and things like this, and this is like spaces them out and does good coverage. Yeah. Good. So we're, by construction, only searching over convex sets. So maybe the answer to your first question is why? How do I know when I'm found a collision-free region that it's convex? Because I'm using separating hyperplanes to separate me from the obstacles and stuff like this. By construction, the sets that I will get out are these polytopic regions that are going to be convex. So that one's just by construction. And then your second question was, sorry. Okay, good. Yes. So why do these regions need to be convex? We have very strong algorithms where I can talk about completeness and optimality in the case where it's convex. There are natural extensions to that which could relax that assumption, but to understand how far we can get with like strong claims of optimality and things like this, we left it convex. So, you know, that's the same kind of question. Why would you do convex optimization versus non-convex optimization? We have a deeper understanding of what you can do with convex optimization. And this keeps me in the land of convex optimization. Okay, so yeah, and then you can just repeat if you miss some spots or you got unlucky because you had a point in the middle of your too sparse convex, you know, you'll just repeat the process until you get a nice coverage. And so it does these beautiful, like this, you might have seen convex decomposition of 3D geometry, right? Like if I have a CAD model and you do a convex decomposition, well, this is an analog, but it's trying to fill in the free space, right? So this is now a three-dimensional version of that problem. The interior of that is the collision-free space, and it comes up with these sort of convex decompositions of the configuration free space. And if you're willing to do that work up front, then we have, you know, and you're willing to keep things convex, then we have a very strong set of algorithms that kind of make that search possible. So the PRM had to do graph search, right? So we just had a discrete point, vertices, edges. We just had to find a path from the start to the goal. Maybe we wanted to find the shortest path from the start to the goal. That's a very well understood problem. We have lots of good algorithms for solving it. So the extension that we've been working on, this graph of convex sets, generalizes that. And the picture, the abstract picture, so these blue regions are not obstacles. This is just like the mathematical construction underlying the algorithm, okay? I'm going to still solve a graph problem. But every time if I choose to visit a vertex on the graph, I'm allowed to pick one element out of a convex set. That's it, okay? And then I'm allowed to, my edge length, which typically would be just a constant, I'm allowed to make a convex function of the continuous variables. So if an edge, in the case of a shortest path, I want to say if this edge is in the shortest path, then I picked one element out of this set, one out of this set, and the edge length is the distance between those points. Okay? It's a very general, say, take any graph, you can add a continuous extension to it by saying I'm going to associate with every vertex a convex set. Just a very general sort of idea. What's cool about it is that we have really strong algorithms for depending on what your graph problem is, but some of them have, like shortest path has a really good solution. And so we could take that really good solution and add this continuous extension to it. And I haven't talked much about mixed integer optimization, but this is a case where you can do mixed integer optimization if you want to guarantee that you found the optimal solution. But we found a formulation that is the convex relaxation of that problem is very tight. So it is NP-hard. You can write NP-hard problems into graphs of convex sets, shortest path. But in practice, we just solve a convex relaxation of the problem, and it almost always finds the global solution in all of the instances we've found. You can write instances that specifically break that, but you have to work pretty hard at it. Yes?
So the weight of the edge depends on like the whatever like cost of that optimization. But it seems like that you need to pick both points within like either set, but like it seems like for like one trajectory or like one thing that we want to plan, we might pick two different parts of the same convex set. Does that not happen in practice? Or like how does this work?
So you're asking all the right questions. So let me tell you, so this is still sort of an abstract graph problem. And now I have to tell you how to take iris regions and turn them in curves and turn them into a graph of convex sets. Okay, so that's the last step. And I wrote a little note, but lots of references. This morning I just started filling in the notes on this, okay? But I could tell you a lot about the optimization that makes that possible, but we're pretty excited about this. This is kind of a new, I mean, it uses ideas that are well known about multiplying constraints and perspective functions and the like, but it's surprisingly efficient and tight relaxations of pretty hard problems. Okay, so now let's think about your question here. So let's say I have the red region, which is an obstacle, the start and the goal, and I have the blue regions, which I'm allowed to visit. Okay, so you're absolutely right. So I don't just want to pick one point in there. I want to put an entire curve in there. Okay, maybe the simplest version of this, imagine I just want to put 2 points in every blue region. Then the straight line connecting them is guaranteed to be collision-free because it's a convex set. That's sort of the definition of a convex set. And then, as long as one of those points, you can put a constraint between the edges. So we're going to make an edge between each of these sets if they intersect at all. Okay? So an edge in the graph happens if the iris regions overlap at all. And then what we do is we put the generalization of that line segment idea, we're going to actually put a continuous curve. We'll use Bezier polynomials. So these are the control points of the polynomial. Remember, it has this convex hull property. It has this nice property that it starts at the first point, ends at the other point, and the entire curve stays inside the convex hull. So all of those points being inside this region, which are convex constraints, okay, forms the convex set. So the convex set in the GCS is actually the set of dimension, if there's 3 control points, it's 3 times the dimension of the original problem. So it's the set, the GCS sees as a bigger set, not the original iris region. The edge says if I'm going to follow the edge from this to this, then the final point of this curve has to be the initial point of this curve. Okay? And then you can add velocity constraints and all the other kind of constraints we know how to add. And you can see, so a solution has to satisfy, for instance, continuity. And then just because once you start talking about velocity continuity, you need time. We don't want to pre-specify what the time is. So we have an extra time parameterization, just like we did in kinematic trajectory optimization. Okay, so you put that together, and here's like a sort of a simple example of kind of this kind of a problem, right? So just trying to find a path through this, of the 2D world, moving through this little obstacle space. Okay, you start with a geometry of your obstacles. You do a convex decomposition to find the blue. And then you solve this GCS trajectory optimization, and you can find this is like the shortest path. If you just have the cost function as time, then you get straight line paths, actually. Because the fastest thing to do is to just take a straight line. If you haven't imposed velocity continuity or anything like this, that's the shortest path. If you start emphasizing smoothness, then you can find a completely different path through the graph because you change the objective function. And this you wouldn't have done if you had just done the RRT and locked it in and then done trajectory optimization, right? So, this is somewhere like our paper's just coming out about this. People are starting to use it. I would love if you guys if anybody wants to try using it in their project, that's fine. I'm happy to help with it. It's just kind of transitioning out of the lab and into like real world cases. So it's all implemented in Drake. You can do a bunch of different sort of costs and constraints, but not everything. So we are being conservative here. We're staying in the land of convex optimization. Okay, but a lot of the costs and constraints you'd want to add, we know how to add or we know how to approximate. Okay. and it tends to give better solutions than PRM with shortcutting, for instance. And oftentimes, because we offloaded the pre-computation of these iris regions, the online planning is actually better. Okay, so it does run on real robots. This one is even planning through the decision of when to pick up the mugs, right? It's actually planning. We can do some amount of multimodal planning and task and motion planning kind of ideas in this. Okay. It can solve problems that you kind of be surprised, I guess, like a quadrotor flying through a maze, right, where the maze can be like arbitrarily complicated, and it solves them very nicely with convex optimization, right? So, and it's not surprising if you think like the path through a maze is just like a discrete graph search, so that's not hard. The continuous curves of the quadrotor, constraints of the quadrotor are continuous things. Those independently we knew how to solve, and what's powerful is that we can solve them simultaneously now. And this is, so DexEye, I told you guys about DexEye the other day, and they put their PRM, which they've been using in products and working hard on, and this is same initial condition, same goal, same whatever, and the point is, I guess, that the GCS is done here and the PRM's still doing their thing, and they have a business model that basically they earn more money the faster they move salad. So they were like really happy about that. Yeah. Yeah, and we're getting to the point where we can scale to big problems, right? So that's the basic picture, is that I think the PRMs have been fantastically successful, and in some cases where you can afford to do, I think the dynamic obstacle cases, GCS has still got a lot of work to do, okay? But the cases where you can afford to do some of this pre-computation, we're understanding now a lot more about how to connect continuous and discrete optimization. This is the thing I was trying to talk about last time. I found a picture, right? So I still don't love collision-free motion planning. I still think it's the wrong problem. So we will talk more as we go deeper into the semester about not being afraid to bump into things in the world, because this game is terrible, and robots shouldn't do that. Actually, this is, so there's like an explicit project at TRI, and you see the sticker on my laptop, actually, of trying to make roughly a version of Baymax that's roughly not afraid to bump into all kinds of stuff. Yeah?
So I think he previously mentioned that if there's like a bottleneck or if there's like a zero degree in the free space, RT and PRM would suffer in finding it. Does this won't happen to GCS as well?
That's a really subtle question, a really good question. So what about these zero-dimensional constraints? So trajectory optimization typically handles those very nicely. That's exactly why trajectory optimization is good at dynamic constraints. Like if you have, if you have an airplane or something that can't take arbitrary trajectories, that exactly manifests itself as zero-dimensional curves in the space that are admissible trajectories. Okay, so trajectory optimization, parameterized correctly, handles those very naturally. Sample-based has to do a lot more work to do it. So in some ways, the trajectory optimization can just address that. So for instance, if you have convex constraints that say you must be on a line inside your GCS, it just eats that for breakfast. Now, if you ran Iris on a thing that was a geometry that had zero dimensions, then Iris will not succeed in that. Okay, so there are still things that could trip it up, but the GCS part would actually work very well. Yeah.
You mentioned that there's issues with dynamic obstacles, and I was thinking about how when you pick up a log or an object, now what position.
Oh, so good. Okay. All right. So that's, I should have even said that. So this is another thing. We were joking last time about how everybody cheats a little bit when they pick things up and they turn off their collision geometry or whatever. Okay. So what do you do when you pick up a mug and suddenly your collision geometry has changed? Like you don't want to smash the mug into something, right? So what do people do in PRMs? They will often make multiple PRMs that have one geometry with the mug in the hand. It may be a conservative box around the things you're going to pick up, and another PRM that has no mug in the hand, okay? And you switch between them in order to do your plans. And you can do all the same tricks in GCS with, and the same. So if you're too conservative with that, then you could trim your roadmaps at runtime because of the new collision geometry. Same thing with GCS, you can trim your regions. So we're really leaning on a lot of the same games that people do to solve that problem. You know, I think if you know you're going to pick up 5 different size mugs, then maybe I'll make 5 different size PRMs, you know, or 5 different size iris decompositions. Or we accept the conservatism and just say I'm going to trim it online no matter where I pick up the object. Yeah, really good. Great, okay. Looking forward to reading your project proposals.